This is a video lesson on the image qualities. So the image qualities include receptor exposure, contrast, spatial resolution, and distortion. Receptor exposure is defined as the amount of radiation striking the image receptor. So looking at the images shown here, we can see that there's different radiation exposures that were used as far as different masses that were used for these, but the overall brightness is the same. So automatic rescaling controls brightness in digital imaging, but the receptor exposure still increase with an increase in mass. So there's factors that affect receptor exposures that include mass, and that's the controlling factor. In addition to that, there's KVP, filtration, beam restriction, patient factors, grid ratio, the anode Hill effect, and SID. Let's begin with mass. So MA sets the number of electrons that we're going to send from the cathode to the anode, and that's the electrons that boil off the filament. Secondly, we have the exposure time, which is the length of the exposure time, the length of time that the electrons will go from the cathode to the anode. Together, this makes up the mass. Mass controls beam quantity, which is also known as intensity and exposure, or the number of X-rays. Increased mass increases receptor exposure. If we take a look at the image on the left-hand side, we see where there's less mass was used, so there's less receptor exposure. In the image on the picture on the right-hand side, we can see more mass was used, so therefore there's more exit radiation reaching the image receptor. The three exposures were taken at 65 kVp. The first one was taken at 1 mass with an EI number of 746. And we can see that when we increased to 2 mass, the second image had an EI number of 1584. The third one was taken at 4 mass and had an EI number of 3215. So as we increase mass, we're going to increase receptor exposure. So quantum noise is a grainy appearance on the image, and what is the cause? Insufficient mass. So the image that you have that was taken below, that one has the quantum noise. KVP is the push behind the electrons, and it controls the beam quality and affects beam's quantity. Increased KVP increases receptor exposure. KVP is the push behind the electrons. So it's going to be the force or the push that's going to be behind the electrons that are going to be accelerated from the cathode to the anode. And therefore it's going to be impacting our X-ray beam. So if you have a low energy KVP beam, we have a long wavelength, and we're going to have less exit radiation. Less X-rays will be penetrated, more will be absorbed. On the right-hand side, we have a high energy or KVP beam, which is high quality. And so we have more radiation or energy that's going to penetrate the part and therefore reach the image receptor. So higher KVP will increase receptor exposure. The three images were taken at 1 mass. The difference was the first one was taken at 55 kVp and had an EI number of 300. The second one was taken at 66 kVp and had an EI number of 659. And the third one was taken at 77 kVp and had an EI number of 1153. And this demonstrates that as you increase KVP, it will increase receptor exposure. Excessive filtration decreases beam quantity. So we have a total of 13 X-ray photons in the top, and we only have 6 in the bottom part. So we've gone from 13 down to 6, which decreases beam quantity, and that will decrease receptor exposure. A smaller field size, which is more collimation, decreases receptor exposure. If we look at the image on the left, the picture on the left-hand side with the smaller field size, we have less primary radiation, and therefore less scatter is produced. And when less scatter is produced, we're going to have less receptor exposure, less radiation reaching the image receptor. The image taken on the left-hand side was taken at 85 kVp at 10 mass, and the collimation was 14 by 17. There was an EI number of 353, and on the image on the right-hand side, the same technique was used, but the collimation was 5 by 5. The EI number decreased to 160, which demonstrates that we have a decrease in receptor exposure with more collimation. A larger patient or part decreases receptor exposure. The first image was taken on the left-hand side at 66 kVp at 1 mass and was a hand, which is a smaller part, and the EI number was 568. In the image on the right-hand side, the same technique was used, but the part was much bigger, which was an abdomen, and the EI number decreased to 32. So larger part decreased receptor exposure. Additive conditions decrease receptor exposure. With the image on the right-hand side, we're looking at the condition of osteopetrosis, in which the bone is more radiopaque. And this is called marble bone, but it decreased receptor exposure. Grid ratio. What's the function of a grid? Well, it's going to increase contrast. The use of a grid or a higher ratio grid is going to decrease receptor exposure. Both images were taken at 85 kVp at 2.5 mass, but the image on the left-hand side, no grid was used, and the EI number was 408. On the right-hand side, the image was taken with a 12:1 grid, and the EI number was 88. So as we go from no grid to a grid, we're going to decrease receptor exposure. And the reason is because scatter radiation is absorbed in the grid, and that was after it was produced, so therefore we're going to have less receptor exposure. The Inotiel effect affects receptor exposure, but how? Well, it's going to increase receptor exposure on the cathode side. The anode acts like its own filter, and it's going to filter out the radiation on the anode side. SID, if you increase SID, will decrease receptor exposure. These two images were taken at 66 kVp at 1 mass. The image on the left-hand side was taken at 40-inch SID, and the EI number was 754. And the image on the right-hand side was taken at 20-inch SID, and the EI number was 2352. So if we go from a shorter SID to a longer SID, we're going to decrease receptor exposure or vice versa. Image contrast. These two images, looking at them side by side, we can see the image on the left is more black and white and the one on the right is more or grayer. If we take a look at this, we're looking at the concept of short scale of contrast on the left and long scale of contrast on the right. Short scale of contrast is defined as the considerable or major differences between gray shades are present, which is high contrast, but the total number of gray shades is small. Long scale, which is in the picture on the right-hand side, is the term when slight differences between gray shades are present with low contrast, but the total number of gray shades is great. And here's a picture showing high contrast versus low contrast. So on the left-hand side is the high contrast where we have the black and white appearance. In the picture on the right-hand side, we have the low contrast where it's gray. Image is gray. So looking at the black and white side, the dog is black and white, the short scale of contrast with two shades of gray, the black and the white. And then the image itself is more as higher contrast as well. So short scale, which is the S, with high contrast, and shall is SH with low kVp. So we have a lower speed of electrons, lower energy or quality in the beam, more absorption with less penetration, more Compton or absorption, more photoelectric interactions with just more absorption, but there's more photoelectric than Compton interactions, which means the image is going to be more black and white. So there's high contrast, short scale of contrast, and a narrow exposure latitude. On the shall, which is the L and L side, we're looking at a long scale of contrast, which is the first L, and low contrast, which is the second L. So the images are gray, which is low contrast. High KVP is going to cause this, and this is when the image has there are higher speed of electrons, there's higher quality or energy, there's a shorter wavelength of your beam, there's less absorption, more penetration, less Compton, which is less absorption, less photoelectric, which is less absorption. There's more Compton than photoelectric interactions, which gives us our gray appearance on the image with lower contrast, gives us a longer grayscale with a wider exposure latitude. The key thing to wide exposure latitude is that a low contrast and a long grayscale gives us a wide exposure latitude. So factors that affect image contrast. We're talking here about KVP, filtration, subject contrast, contrast media, beam restriction, patient or part thickness, grids, and OID. So looking at KVP, 60 KVP provides an overall black and white image which has higher contrast, and it has a short scale of contrast. In the image on the right-hand side, we're looking at 80 KVP having been used, and with this one, the contrast was low with a longer scale of contrast, so the image overall was gray. Excessive filtration will increase beam quality, and when that does that, that's going to increase the beam energy. And just like when we increase KVP, we have higher energy and we decrease contrast, excessive filtration will do the same thing. The use of contrast media will increase image contrast. Contrast media, whether it be air or barium or iodine, the purpose is to increase contrast. And so that's why contrast media increases image contrast. It either provides white or black to the image. Higher subject contrast will increase image contrast. In the images shown here, we've got an abdomen on the left-hand side, which is grayer, and the chest x-ray on the right-hand side, which is more black and white. Therefore, the chest x-ray has higher subject contrast with a higher image contrast. An increase of scatter on the radiograph will decrease contrast. Well, why? Well, because scatter is going to appear as fog, and fog is gray. And so scatter decreases contrast always. Beam restriction. So if we restrict the X-ray beam or have a smaller beam, we're going to decrease the production of scatter in our patient. So anytime we decrease scatter, we're going to increase contrast. So if we decrease scatter, we're going to increase contrast. And these images shown here is that we have collimation, just shown down here at the bottom, that shows that we're going to increase, we're looking at increasing contrast compared to the top image. An increase in beam restriction, which is more collimation, will result in higher contrast. And why is it? It's because scatter is decreased before it's produced. A larger patient or larger part will decrease image contrast. Why? More matter, more scatter. So we're going to get a lot more scatter on our image. Grid ratio. The use of a grid or a higher grid ratio is going to increase image contrast. And why is that? Because scatter is decreased after it is produced and before it reaches the image receptor. We take a look at the image on the left-hand side. No grid was used at 85 kVp at 2.5 mass, and the EI number was 408. And we have a lot of gray, which shows that we have low contrast. In the image on the right-hand side, the EI number was comparable, but a 12:1 grid ratio was used. The technique was increased to 85 kVp at 12.5 mass, and we can see that we've increased contrast by using a grid. We've decreased the scatter after it was produced. An increase in OID increases image contrast. Well, the reason why is because scatter misses the image receptor. What is the term using increased OID in place of a grid? It's called the air gap technique. So there's a built-in air gap between the shoulder and the neck, and so for lateral C-spine, we use the air gap technique. In order to decrease magnification, increase receptor exposure, we increase the SID. Spatial resolution. This is the sharpness of a structural edges recorded in the image. And sharpness is defined as the lack of spatial resolution. So we're looking at the fine details at the edges of the image. The factors that affect spatial resolution include motion. Then there's 3 geometric factors, which include focal spot size, SID, and OID. There's also patient or part thickness, and then the angle of the tube part or receptor. Motion decreases spatial resolution. The reason why is because the image is blurry. When we look at the electron beam size, that's the size of the electron beam where we have the electrons coming from the cathode. The actual focal spot is the area where we have the dotted lines here where the electrons actually strike the target. And the effective focal spot size is the area to which the X-rays are projected to the image receptor. It's also called the projected focal spot. So the dual focus tube in diagnostic radiology has a large focal spot and a small focal spot, and the large focal spot is where we use the large filament and the small is where we use the small one. The large focal spot size decreases spatial resolution, and that's because the divergent rays spread out before they strike the image receptor. SID and OID. SID should be maximized or should be longer, and OID should be minimized or should be as short as possible. A longer SID increases spatial resolution. So as we have a longer SID, we're going to have less unsharpness at the edges of the image. A shorter OID increases spatial resolution. If we look at the picture on the left-hand side where we have the longer OID and looking at the shadow and how large and how blurry it is, but compare that with where the ball is close to the image to the floor, and we can look at the shadow now there's less unsharpness. And so that's the factor of having increased spatial resolution. The smaller or patient part is going to do the same thing because it's going to be the same result as the shorter OID. So it's going to increase spatial resolution. The angle, which includes the tube, the part, or the receptor, affects spatial resolution. Next, we have size distortion, and the factors that affect size distortion include SID, OID, and patient factor, which gets into the size again. So the SID, the longer SID decreases magnification. So we're going to look at the source, the SID, the source image receptor distance on the right-hand side, and we get a smaller size part. Specifically, these images were taken at 40-inch SID with 3.5-inch OID, and the image on the right was taken at 20-inch SID and 3.5 inches OID. And we can see the difference in the magnification between the two, so that is longer SID is going to decrease magnification. A shorter OID decreases magnification. So looking at the shadow again, we can see how much smaller it is with a shorter OID. And the same thing happens with a smaller patient or part. It's going to decrease magnification. The two images were taken at the same technical factors and the same SID, but the OID was 3.5 inches for the one on the left, and the one on the right was taken at 7-inch OID. And we can see that there was an increase in diameter from 1/2 inch to 1 inch between the two images of the quarters. Shape distortion is our last factor, and that's the factor that affects shape distortion is the angle, the tube part, or receptor. The two types of shape distortion are elongation and foreshortening. So foreshortening is caused by the part is tilted while the tube and the receptor are perpendicular. And elongation is caused by either angling the tube or the tube is directed perpendicular to a part that is tilted in relation to the image receptor. If we take a look at the three images here, the central ray was perpendicular to the quarter, and the quarter was parallel with the image receptor for the first, and so the length and the width of the quarter were equal at 3.5 inches on each for each. In the middle, we've got an image that was taken with the central ray was perpendicular to the image receptor, but the quarter was angled 45 degrees. Therefore, we had shortened up one axis, which was 2.5 inches, and the other one was 3.5. So this is foreshortening in the center. And this image on the right-hand side was taken with the central ray perpendicular to the quarter, and the quarter was angled 45 degrees. This time the length increased to 4.5 inches from 3.5 from the very original. So this is referred to as elongation. And this concludes our video lesson on the image qualities.